Welcome everyone who's joined us. Once again, this is Seth Grimes, the organizer of the Maryland Artificial Intelligence Meetup and Baltimore Tech. This program is cross-listed between the two meetups. We've been around for a year and a half now and have moved to online programs such as this one. So we're going to aim to do online programs every twice a month, really. Once a month, it will be a program like this with a guest speaker. Today we have Ashley Llorens from the Johns Hopkins University Applied Physics Lab. And then we will also be having roundtable discussions of TEDCO, the Maryland Technology Development Corporation Artificial Intelligence Roundtable, which I moderate. We'll have those sessions online as well. So we'll have one of those coming up in 2 weeks. So once again, let me welcome you here today and thank in particular Amazon Web Services for sponsoring the meetup, helps cover costs and all of that kind of stuff. In particular, we're going to have a short talk by Jamie Hansen, who is an AWS recruiter working here in Maryland. I do have one very short commercial pitch for you myself. Among the things that I do is conference organizing. I have a conference coming up next week, the Emotion AI conference. This was originally going to be on March the 30th in New York. Well, that wasn't feasible. So I've moved it online, which means that you can attend from your home office or wherever you're working, from here in Maryland or wherever it is. And I'm happy to extend to Meetup participants a 20% discount via the Meetup registration code. Conference is online at emotionai20.com, where you can look into the speakers. The speakers, this is a technology conference, will cover natural language processing, speech technologies, facial coding for emotion recognition, wearables, neuroscience, as well as a panel on brand concerns and another panel on data bias and ethics. So it should be really interesting, and I'd invite you all to attend. So we're going to go now to have a word from our sponsor, Jamie Hansen from Amazon Web Services, who will just speak to you for a couple of minutes before we get to our main speaker, again, Ashley Llorens. Jamie, you can share your screen. I see you're doing that.
Super. Thank you very much, Seth. I appreciate the meetup and the opportunity for AWS to sponsor. I'm actually the practice manager for AWS's National Security Professional Services practice. We support Fort Meade and Cyber Command. So we build mission systems using AWS commercial and IC cloud services, technologies, and best practices. So our team is literally changing how DoD builds NatSec mission tools. I'm the practice manager, but I put out my flair down there to say I'm also a builder, just like everybody else at AWS. We are a hands-on keyboard group from all levels. I'm also a Marylander, a Terrapin, and from the USAF. So I'll own, I'm here to talk. We're looking for really, really smart, cleared people who know AWS. We're looking for folks who want to use commercial relevant skills, but in a cleared environment. And of course, folks who have a passion for the national security mission. We're only able to talk to folks who are cleared and eligible to work at Fort Meade. If this is you, your friend, your colleague, your neighbor, your niece, your nephew, please reach out to me. Jamie Hansen, that's Jameyh at Amazon, Jameyh at Amazon. My partner in crime, Chris Widman, he's our senior recruiter, he's here. Also go to amazon.jobs. Location is Annapolis Junction and the position is cloud consultant. Or join us tomorrow, the link is there. We have 3 to 5 a recruiting event. Now I'm looking forward to hear what Seth and Ashley have to say, so thank you.
Thanks, Jamie. I'm not going to have a whole lot to say, but I will say that I will send out information on a few of the positions you have open as we discussed to meetup members via message after the meetup. So let's move to our speaker for the day, who is Ashley Llorens from the Johns Hopkins University ISC, is Intelligence Systems Center. Let's see, I guess I got that right. And I heard him as part of a panel last March, I'd say in 2019 in Baltimore, an AI panel. A couple of my friends were participating in it, so I went along and I was quite glad I did. And I'm very glad that he is here to speak to us today about the activities at his center. I'm going to allow him to introduce him further. I can't really tolerate moderators who read off canned bios when you have a person right in front of you who can say something more easily about himself. So Ashley, take it away. I will invite everyone to enter questions via the Q&A function in Zoom. You can also feel free to use the chat function, and we will monitor that. It's up to Ashley whether he wants to take questions during the talk or afterward. And I hope we'll spark some discussion here. Ashley. Hold on. Okay, sorry. Okay, take it away.
Okay. Well, thanks for the opportunity to engage with this group. I'm passionate about AI. I'm also a resident of Maryland, as it turns out. And so very happy to see you know, an investment being made here and building this community of practice in Maryland. And so hopefully, you know, I'll hear from some of you during this talk and maybe afterwards. Really interested in hearing about what you guys are doing as well. As Seth mentioned, I'm the chief of the Intelligent Systems Center at Johns Hopkins APL. I'll talk a little bit about those two organizations in a moment. My own background is in machine learning, mainly applied to autonomous systems, and in particular in national security and health applications. Again, I've been at APL for about 17 years and in this field, and have seen, I guess, multiple waves and generations of AI and machine learning. So it's been an interesting ride and certainly gotten even more interesting recently. All right, a few words real quick about Johns Hopkins APL and the ISC. APL is a not-for-profit research and development center that does a lot of contract work for the government and other sponsors as well. We're a university-affiliated research center, which means, again, a division of Johns Hopkins, not primarily concerned with teaching, although we do some of that, but primarily concerned with developing systems. And that's our about 400-acre or so campus for our 7,000 or so folks in Howard County on the left. And on the right is the Intelligent Systems Center. Now, in different times, it would have been great. You know, this could have been a good field trip for the group, maybe to come visit. Maybe we'll do that sometime. But for now, maybe we can sort of fly into the front door here with this video, show you a little bit more about what we do. So it's not atypical to see me standing in the lobby like this, talking to groups like this about what we do. This is a 40,000 square foot facility that houses a 100-person research group that does AI, robotics, and applied neuroscience. It's an open concept, and so it feels a little bit more like a startup than the rest of APL. And you'll see we really put a premium on taking new research ideas in these different disciplines from concept to exploratory research, prototyping, simulation, to prototypes that we can build and actually test. And I'm going to go zoom through some of this and get back into the test area that we use to actually test some of these systems out. And it's a nice intermediate stage between, again, initial concept, things we do in a computer, to being able to, put an algorithm on a system, fly it around in this kind of netted area in front of a motion capture system, and to do lots of different kinds of prototyping and experimentation in the space. So that gives you at least a little bit of a window into the physical space, some of the core disciplines and the various capabilities. And then in the slides, I'll expand on some of the research projects. All right. Interwoven with these research projects, I also want to cover a little bit of our philosophy on AI and how we think about it. Especially recently, I've had a lot of, I place a lot of emphasis on human beings as the point of any technology development, including AI. And I like to talk about AI in the context of human agency. You know, as human beings, what we really want to be able to do is set goals for ourselves and to be able to accomplish those goals. And what we want technology to do is to help us do that. And so that's how we think about AI. If intelligence is the ability to accomplish complex goals, then artificial intelligence is that ability in machines to accomplish complex design goals that help human beings achieve our own human goals. So that's how we think about intelligence and AI and the role of AI. So Johnny here, this is a nice illustration of this. Johnny here is is an amputee and a longtime collaborator under a DARPA program called Revolutionizing Prosthetics. And so Johnny's goal is to be able to manipulate objects in the physical world as he could before he lost, this part of his arm. And so this robotic prosthetic limb is really designed to help him do that. In order to do that, it needs to be able to perceive the world, the operating environment for the system, to make decisions on the courses of action to follow that best help to pursue Johnny's goals, to act, to carry those out, to affect the world in some way, and to do so as part of a team. Perceive, decide, act, and team. And so for this modular prosthetic limb, the operating environment is actually Johnny's nervous system. And so it uses this myoband sensor to sense that activity, to make a decision about what Johnny's motor intent is and how best to move itself to carry that out, and then actuates itself accordingly. Now, Jen in the back is remotely commanding Robo-Sally, this hybrid kind of centaur-like system here. And it's doing a version of the same thing. It's perceiving. In this case, it's doing a remote perception of Jen's hand with an IR sensor. It's deciding on the intent and the best mapping of that intent into its own physical space, and then acting to carry that out in this teaming relationship with Jen. This is a nice illustration of kind of the human-machine relationship, the goal of machines, which is really to help us achieve our goals, and the constituent capabilities that they need to do that: perceive, decide, act, and team. And now, humans don't always have to be in the loop, so to speak, as you saw on that slide. This is an example of research we've conducted over a number of years into autonomous marsupial robot teams. And so this is the same centaur-like system, Sally. This time, instead of being in the loop, closely following kind of motion commands from a human beings are outside the loop. And so the idea is that you would task a system like this with multiple robots. We got Sally carries a flying robot that carries a smaller ground robot, and that they can make autonomous decisions about how best to pursue the goals given to them by a remote, a team operating remotely. So here's an experiment that we did in that large test area in the Intelligent Systems Center that I talked about. This was maybe 2 years ago now. And the idea here is that you've got a room, and the configuration of the room is not known to the people or the robots ahead of time. At the same time, maybe there's a floor plan, and so the people can take this gray map that follows the floor plan and say, hey, robots, get to this corner of the room and tell me what you see. And then the robots carry that out. And there's navigation tasks in there, perception tasks, manipulation tasks, et cetera. And the robots will allocate intelligently the subtasks to the different robots based on the different capabilities. And so at one point, there's a closed door between the system and the goal point given by the operators. And so they make a decision that Sally's going to be the one to open the door because she's the only one with that manipulation capability. Sally opens the door, realizes she can't fit through, and then tasks the Pelican UAV to fly in. All of these systems are running LiDARs, mapping the space, running computer vision algorithms, and then relaying back this three-dimensional map that's being created, as well as objects located in the scene, and then having a human-machine interface. And so again, these systems perceiving, deciding, acting, and teaming, always in some relationship with human beings, although in this case, the humans are farther outside of the scene. And what that does is it creates a larger and more complicated world that the systems need to be able to perceive and understand, a larger space of decisions that the system has to choose from among to pursue this course of action in a different kind of a teaming relationship. Okay, and so, the expanse of our mission set at APL, the picture on the left, the 7,000 person organization, really spans national security, space exploration, and health. And we think advancing AI with this philosophy will really help us have mission impact, further mission impact across this mission space. So I can see the chat window lighting up with some questions, which is great. I think I won't be able to read the chat window and read my slides. And so I would invite you, I don't know, Seth, if they're able to.
That's actually me. I was sending a message to some people, including you. So I was concerned that the wrong video feed is showing in addition to your presentation. But so keep going, please. Well, Ashley looks frozen to me. We may have lost his connection here. Sorry, folks, about this. I've done half a dozen of these programs now, and it's inevitable that some kind of problem is going to crop up sooner or later. Yeah, I'm sorry. It looks like we lost Ashley there, and he's reconnecting. So just be patient for a moment, and now you're good. Ashley,
Hey, Seth,
you're
this
good
is
again.
Ashley again. Can you hear me?
Yes, you want to restart your sharing. You need to restart
Seth,
sharing
I
your
cannot
application.
hear you if you're talking to me.
Ashley, are you able to hear me?
Ah, I can hear you now.
Good. So you need to restart sharing your application,
Okay.
your presentation, that is. Sorry about that, folks.
All right, let's see. There we go. All right, Seth, what was the last thing you heard me say?
Sorry. Sorry, I'm not going to be able to help there. Just try to pick it up as best you can.
Okay, that's fair enough. I think I saw some questions in the chat window. If people can interrupt me with audio, please feel free to go ahead and do that. I don't think I'll be able to kind of read the chat and talk. Otherwise, I'll try to leave ample time at the end for questions.
So if anyone wants to speak a question, raise your hand using the Zoom raise hand feature, and I will allow you to speak. I have to intentionally do that.
Okay.
Continue, please.
And I welcome those interruptions. Okay. So hopefully you saw the vignettes that I showed that kind of talked about this human-centered view of AI and gave examples of AI and helping humans achieve their goals in close proximity, like prosthetics, and then farther removed in time and space, say through autonomous systems. And then I put up this slide and said, you know, these technologies we think will have a profound impact across the mission space that APL pursues: national security, space exploration, and health. And so our job in the center is to really try to stay at the cutting edge of advancements in those technologies, get up to, you know, research and proof of concept experiments, and then work to translate those technologies into the mission space in partnership with more applied folks in the rest of the organization. This is our roadmap for artificial intelligence. And what it does is it takes that framework, perceive, decide, act, team, and trust, and develops near, mid, and far-term goals associated with those. So for perceive, we want increasingly autonomous perception, machines able to understand the physical world on the basis of their own sensing and reasoning, superhuman decision-making and autonomous action, increasingly so over the next few decades. So this time scale is, you know, the next few years, the next decade, and decades tend to infinity kind of thing. Because this is really, you know, that outer horizon is really really the frontier of what we think we might be able to achieve. As I was kind of pointing out, every machine is part of a human-machine team, and so as we increase the sophistication of the AI and the systems that it empowers, we need to bring the human-machine partnership along for the ride and increase the level of intuitiveness and the level of effectiveness of human-machine partnerships. And then meanwhile, all of this creates an increasingly complex test and evaluation and ultimately trust issue, especially if you're going to employ these systems in real-world applications that may be safety critical or life critical. And so again, we envision an advancement, a progression of advancements along this trust dimension as well, safe and assured operation. So this is our roadmap, and this really helps us establish these pointing vectors towards future capabilities and how we want to progress in exploring them. So far I've talked a lot about AI. I haven't talked much about machine learning. Our view is that deep learning is a subset of machine learning, which is a subset of artificial intelligence. So even though we often see the letters jump, mashed together, AI/ML, we see ML as part of a family of techniques that we use to design systems. Systems do not consist typically of a single algorithm. They have architectures with many components that work together to create the behavior of the system. And so the real benefit of machine learning is to help us design components of systems that we can't design explicitly, either through declarative, instructions, lines of code, or analytically with math and theory. So this is an example. I'll play this video, and I'm sure folks are, kind of up to speed on recent advancements in deep learning. But obviously, a computer vision module like this is one that we don't know how to create explicitly, that machine learning helps us create. And so as I play the video, just that mapping of pixels to analytics about those pixels is amazing and is a recent development. But there are also some important limitations to these kinds of capabilities, and I'll hopefully that'll be illustrated in the video here. All right, so this is my colleague Neil. He actually programmed this vulnerability into this computer vision algorithm for illustration. So in effect, he poisoned the data set by taking half of the people in the data set, adding this pattern, and labeling them as teddy bears. Now, if I took away the data set and I just gave you the trained neural network and said, is there such a vulnerability in this neural network? No one knows how to answer that question just on the basis of the weights and the trained model. And so whether these are kind of edge cases imposed upon us by the natural world or the result of tampering, for example, it's really hard to tell what's happening inside the deep net from a safe and assured operation standpoint. So this is an important area of research for us. We're doing some internally funded research here, and also some, actually many different research efforts in partnership with the government. IARPA is one of our sponsors, for example, on a program called Troj AI. And Mike Wolmitz is my colleague that can tell you more about that effort. Let's see. So one of the things we're trying to do is create machine learning algorithms that are more robust through incorporation of multiple modalities and by combining world knowledge of different forms with machine learning algorithms. And I think this is well illustrated. This is kind of a snapshot of a tool we've developed called Active Sensing Testbed, where we integrate kind of leading edge algorithms coming out of academia, and then also some of our own, and see what we can achieve by putting lots of them together in the same kind of real-time environment. And so this is multiple feeds. So this one on the lower right is my colleague Lee, who built this tool. And this is him in our Intelligence Systems Center. This is a live feed from New Orleans. This is a live feed from London, and this is from New York. And so this is just the kind of things this environment can do. And instead of putting bounding boxes around the people, what we're running is an algorithm from the literature called semantic instance segmentation that's actually trying to paint each pixel in the image according to object classes that it thinks it belongs to. And so it's not putting bounding boxes around the people. It's actually saying, these are all the pixels in the image that it thinks correspond to people, and it's labeling them accordingly. The other algorithm that's running is called Open Pose, and it's a pose estimation algorithm. And what I like about this algorithm is it's actually doing some geometric inference. So if you see these people walking around, you'll see this sort of stick man being progressively estimated and kind of following them. And you can imagine taking these different analytics, having different kind of sensor modalities, you can create algorithms more robust to the kinds of vulnerabilities that I showed on the last slide. So this is just a really small example of what progress along that autonomous perception vector might look like, incorporating multiple modalities of sensing to do inference, multiple kinds of analytics, and combining learning and world knowledge. And so I throwing this out there again just as an illustration of the kinds of things we're interested in, and also just showing you we have this environment that is really cool research and innovation environment for us at the center. The other thing I want to, so I'm going to kind of walk through advancements in the order of this framework. So perceive was the last slide, now into decision making. And so we've seen advancements not just in the ability of machines to learn patterns in data through supervised learning like what I've shown, but also for machines to learn autonomous behaviors through techniques like reinforcement learning. And so in that case, the function mapping we're accomplishing is not just pixels to analytics about those pixels or analogous kinds of problems, but mapping input states to actions and learning functions we call policies. And that kind of approach is responsible for the recent advancements like AlphaGo becoming the world champion in Go, for example. One limitation to many of the popular reinforcement learning environments in games is that they don't necessarily incorporate uncertainty. And so for many of our real world applications, uncertainty is something we care about a lot, and we need algorithms that can handle that. If you think about that big game tree for Go, the game of Go, where as each player makes moves, the number of possible moves that could have been made kind of expands exponentially on order of 100 per step. And so that's an enormous game tree. But if you add in uncertainty, then every node in that tree is not just a singleton set, but is a hypothesis, a hypothesis class or an information set of possibilities that need to be reasoned over. So that's what we're considering in this chess game that we created. It's a novel variant of chess we call reconnaissance blind chess. And so in general, you do not get to observe your opponent's pieces except through sensing actions. And so if you're black here and white has moved, then what this is an illustration of is all the possible board configurations that could be after that first move. Black gets a sensing action of a 3x3 square of the board, and if correct, collapses this information set down to a singleton. And so this sense move dynamic happens throughout the game. It turns out if you look at the complexity of that game and you compare it to one like Go, where chess is typically a less complex game than Go, and you consider all the additional complexity of the uncertainty and the opponent's knowledge, so you don't know what the opponent knows about you. And so all that additional uncertainty on the board state and the opponent's knowledge actually winds up making it a more complex game than Go in that respect, in terms of just the number of possible states that the board can be in throughout the game. So this is a game we've been experimenting with and doing research on for several years at APL. We have thousands of people, so we can run pretty interesting challenges even inside of our organization. But last year, for the first time, we did a challenge outside of the organization for the world through the NeurIPS conference, the Neural Information Processing Systems Conference. So this is a picture of our team and some of the winning participants in our challenge that came from places like Google, George Washington University, et cetera, et cetera. There were about 60 competitors from around the world. And it was really interesting. And so we just published a paper in PMLR talking about what happened with that. But what I want to share with this group is that it was so cool, the result, and there was such good interest that we're actually running a follow-on challenge on our website happening right now. And so you can go to rbc.jhuapl.edu. You can use the interfaces available there to create your own reconnaissance blind chess bot. And there's a leaderboard now where the bots are kind of playing each other, and they get ELO ratings as they win and lose against each other. And at the end of the fiscal year, around the end of the fiscal year, we're going to give $1,000 to the developer of the first place bot by the end of that period, and $500 for the second place bot. So if AI games and decision-making under uncertainty is your thing, we invite you to come and join us in this. We're having a lot of fun and learning a lot as well. So I talked about reinforcement learning in the context of games. And another kind of frontier for us is taking reinforcement learning into learning more like behaviors. So not just long-term strategies in kind of pristine game environments, but getting into more complex simulations that have physics and things like that. So this is a tank game we're developing in an environment we call AI Arena, which allows us to look at multi-agent reinforcement learning in a number of different simulation environments. So this is Unity, It's got an underlying physics simulation. And these agents, this is a team-on-team tank battle, red versus blue, and there's some kind of innocent bystanders in there. This is this green. So blue's job, for example, is to eliminate red without taking out its teammates and without taking out the innocent bystanders. And so what this forms is a multi-objective learning problem. And this helps us to explore, first of all, unintended consequences, but also reward shaping when you've got multiple objectives. And so what you're going to see then is, in a really aggressive tuning of this algorithm, this blue guy is going to be kind of get really aggressive, and it's going to accidentally take out its teammate and this innocent, quote unquote, innocent bystander over here. So these are learned behaviors, not explicitly programmed behaviors, learned through reinforcement learning. So you see there's some casualties there. They're effective in taking out red, but they have many unintended consequences as well. When you shift the emphasis in the reinforcement learning reward function to safety, away from mission, accomplishing the mission, they learn because reinforcement learning is about taking random actions and then learning which ones do well. They point their guns away from the whole action because they take random shots every once in a while, and they're really safe, but they're not very effective. And so this is a nice kind of multi-objective learning environment where we can explore the state of the art in machine learning, and then how you start to incorporate things like safety when you learn machine learning. And so this is a competition actually that we're hosting now internal to the lab, and developing some nice baselines, some initial findings. And then we hope to open that up to the external community as well, perhaps as early as next year, next fiscal year. So our framework, I'm just walking through, perceive, decide, and then act. And so I showed a progression over the last few slides of, kind of AI in board game environments where, there's really no mystery. If you want to move the queen a square, you move the queen a square. There's no physics to reason over anything, to simulation environments where we're trying to use reinforcement learning to develop behaviors where there are physics at play, even though it's still simulation. And then eventually we're going to want to put that on a system. And we're going to want to understand the intersection between what we can do with kind of leading edge, I'll say traditional kinodynamic planning and robotics techniques married with some of this reinforcement learning. This is just the latter. I'm sorry, this is just the former, kind of leading edge traditional robotics and planning under uncertainty. And this is the work of Dr. Joe Moore and others in our center. And so what they're doing, I'll show you again what's happening here. This is a YouTube video, by the way. There's a kind of a fixed wing plane. And what they want to be able to do is create aerobatic maneuvers with this plane to do things like navigate really tight indoor spaces. And so what this plane, the a priori information that it has in this space is a pretend map that kind of mimics hallways with turns. And so that's the space it thinks it's in. And it's trying to develop, it's trying to do motion planning on the fly in a way that allows it to navigate that really tight space, autonomously, of course. So that's what you're going to see. And this is inside of that netted area that I showed you before. So it thinks it's in a building with a hallway, and it's actually learning, it's actually developing a motion plan on the fly to navigate that environment. And so this really, I mean, this is publishable robotics research. I think, maybe the research step beyond this is, again, to understand how you marry the best of these kinds of traditional robotics techniques with machine learning when you're designing real world systems, again, that are more than just a single algorithm, that are architectures, with many modules, competing objectives, and systems that have to operate safely. All right, and then finally what I'm going to do is I'm going to just play a little bit of this video, which is a really cool program we're working currently in the center with DARPA called Air Combat Evolution. And a lot of these kind of notions come together where on this program, DARPA is trying to develop an autopilot for air combat missions in dogfights where, you can have something like a reinforcement learning policy or some hybrid solution where a pilot can throw the plane into autopilot, a tactical autopilot, and have it take a lot of these maneuvers on its own. And that's well beyond what what the algorithms can do today. This is another YouTube video.
It's hard to believe that this is our job and we're getting paid to do it. I'd be doing it for a hobby if I wasn't doing it for DARPA.
We're really excited to participate in the trials, and we're looking forward to see who wins.
This is a fantastically run competition.
I have lost Ashley's sound and his video sound.
Engagement, otherwise known as a dogfight.
We are here at the Alpha Dogfight Trials to see if we can get algorithms to perform at a level that human beings would eventually trust one day.
8 technically and organizationally diverse teams were selected to test their intelligent, autonomous agents against an APL-developed adversary agent in a series of simulated dogfights.
Even though we're in first place, our agent still came in slightly lower than our expectations. We actually wanted it to be better.
We're definitely going to take a look at our ground avoidance routine, as well as our bank to turn routine. Alpha Dogfight Trials are a subset of a larger program inside of DARPA called ACE, the Air Combat Evolution Program. And in ACE, what we're trying to do is demonstrate scalable, trusted human autonomy for air combat.
All right, so you can see more about that work on YouTube. It's interesting. Before recent events and the kind of the quarantine, this team was headed to Vegas, where they were going to do kind of the third in the sequence of Alpha Dogfight Trials. And now they're kind of planning what they're going to do for trial number 3. They've done 1 and 2. But you can see again where a lot of these constituent technologies, the use of the center all come together to do something really cool here with DARPA. And there's, this is one of a number of different programs where we're, trying to put AI to work in the mission space. So let's see. I just have one more slide and I'll stop there. So, finally, trust is the last aspect of the framework. And I just want to give a nod to the fact that, even if you can get a machine, to do some really complex behaviors, backflips or, aerobatic maneuvers and all of that, getting it to do it, for a video or for a number of experiments for a paper is one thing, but being able to establish the assurance around that system as it gets deployed in the mission space, that's a whole different thing. Because now you're not just trying to get it to do, a behavior under a controlled, in a controlled experiment. You're trying to understand how, the range of possible outcomes when a very complex system gets driven by a very complex, uncertain, and unstructured environment. And so we're in the process of bringing lots of tools to bear. For example, simulation environments that can adversarially configure themselves to find edge cases, programs that look at how you sample the boundaries between where systems perform well and where they don't to inform real-world testing, advances in theory that help us understand how you take a large body of simulated trials with a small number of real-world trials and start to build assurance arguments from that. Formal methods, so these are kind of black box techniques where you don't necessarily know the inside of the system. Formal methods, when you do know the inside of the system, can you use that knowledge to kind of bound the range of different outcomes? In this case, this is a project done over many years with the FAA, the Federal Aviation Administration, to create assured pilot advisory systems, onboard pilot advisory systems for airspace deconfliction. And then finally, the idea of having assurance monitors on board. So whether you've got a black box system or kind of a human controlled computer advised system, having something like a governor that can look for different exceptions and then engage remediation behaviors to handle those. So think about, a UAV on a test range, and maybe I've got a neural network that I learned through reinforcement learning that I want to try to test out behaviors. But the one thing I can't let it do is go off the test range. And I'm not sure if there's an edge case lurking in that neural network. But what I have maybe is a simpler robot, for if you will, between the neural network and the vehicle controller, doing things like geofencing. It understands where the system is. It understands where the system's supposed to be. And if it wanders out of that, the simpler robot, the onboard monitor, takes control and drives it back on the range. So that's a simple example, but really any kind of exception that you can declare, you can monitor for and initiate a remediation behavior. So that's just a glimpse into the test and evaluation portfolio that we've really been using for years and are now really adapting to try to handle these increasingly complex systems and the increasingly complex missions that we want to engage them in. So, okay, that is all I've got. And I think this would be a great time to transition over to questions. I'm gonna stop my screen share, and then I'll bring the slides back on if people want to ask particular questions.
Okay, I do not. Okay, I have a raised question from Babila Lima. I am going to allow you to talk. You should be able to talk now, Babila.
Yeah, can you hear me?
Yes.
Thank you. Thanks for this presentation. It was really, really informative and really, really helpful. I really liked the slide you showed where you sort of talked through the project and priority areas and the different levels sort of inherent in those in your sort of program and project. That was like really clear. I wonder if you can sort of maybe go back to that and just like speak a little bit about how you arrived at that as like, this is what we will use to communicate through the organization, how we think about sort of projects and priority areas.
I love your question, because this is this roadmap is kind of my baby. This was the result of a year-long effort. And so there was a process that we underwent where we said, okay, we have 12 different mission areas at APL spanning national security, space exploration, and health. And so what we did was we curated a set of envisioned futures for each one of those missions. So we looked ahead decades and said, what kind of capabilities can we envision decades in the future that could be uniquely enabled by advancements in artificial intelligence? Okay, once we had that, we said, okay, we created this framework, this intelligence systems framework, perceive, decide, act, and team, as kind of a trust, as a canonical set of capabilities and considerations associated with how AI would enable those futures. And so then we mapped the specific capability needs onto that space from each of those futures and synthesized it into this roadmap, broke it into near, mid, and far advancements. So that was the process. Maybe it sounds very scientific the way I say it. It was art and science, right? Trying to do this in a structured way. But there was many evolutions to get here. And so we think in some sense, these vectors are somewhat canonical in that, they embody this basic set of capabilities that any entity needs to be an agent, that is to perceive and understand the world, to make decisions on how to pursue course of actions, to act in a way that affects the world and brings it closer to, the system design goals, to do so as part of a human machine team, and to be worthy of trust through some combination of design and test. So this is kind of a little bit of the philosophy behind it, and perhaps I can share more at a later date. I'm sorry, Seth, I cannot, I actually can't hear you on my end.
Yes, I slipped up and didn't unmute myself. So I have a question for you about something that's very much on all of our minds. You show a lot of hardware in your presentation. We're working from home. How has the situation, have you put a lot of your programs on hold effectively? What's the outlook for recovery of this and similar types of programs?
Right. So they're actually, being a defense contractor, we're considered essential personnel at APL. This was just the directive that came out of the Department of Defense. We do, in addition to a lot of the open research that I've shared, we obviously do a lot of sensitive government work that can only be done on site. So APL is many of us as possible are staying home, but the ones that actually have to be on site, especially the ones that are doing sensitive government work, they are on site. Within our center, many of us can work from home, but those of us that still need to be working with hardware and systems are kind of on a schedule coming in and working as we can. So I don't think there's many programs that are necessarily halted. Things are kind of slowing, but my view of the world is I don't think we're going to be out of this mess anytime soon, right? And so we're really trying to envision what that new normal is for those of us that can spend a lot of time off site, for those of us that have to be on site for various reasons, and I guess kind of navigating. But most of our work is not necessarily stalled, but is moving forward at the pace we can manage.
Yeah. All right. Thank you.
Sure.
So do we have any other questions for Ashley or any other comments? If you, I'll give you a last chance. If you have something you want to say, raise your hand and I will allow you to speak. Otherwise, you can use the Q&A function. Otherwise, any takers? I'll count down to 3, 2, 1. Okay, well, thanks Ashley for participating today. And I found this really an interesting view into some pretty cutting edge work. Okay, we did have one question. Do you recommend anything for biology majors? And Ashley, actually, maybe you can more generally address if people want to get involved in the APL work in the Intelligence Systems Center, how do they go about it? You just advertise jobs like any other employer? What's the best route in? So biology work, and then in particular, what's a good route in?
Yeah, we definitely have job openings now. So the best way to see the job openings that we have is to go to our website, jhuapl.edu. And just go to the careers section of the website, and then we just have every open requisition at APL is in there. You can go to this Intelligent Systems Center site. This has got kind of a curated set of requisitions associated with artificial intelligence and the kinds of technologies I saw there. But it's just a cross section of the broader set of opportunities available for APL. We have biologists, we do health work and, epidemiology type work. I don't know if you guys are familiar with the health surveillance work and the Johns Hopkins dashboard that when CNN shows the tallies of, test cases and, positive results and all of that, that's some of my colleagues working with colleagues at Johns Hopkins University. So there's also, I guess, a aspect of looking to biological systems for inspiration for the next generation of AI systems. And so that's why we employ, neuroscientists, people that think about human physiology, also some people that think about animal physiology and animal biology. And so there's many routes in general, and some of them are for people that do biology.
Very good. All right, well, thanks again, Ashley. We'll wrap up now. For everyone else, we'll be doing this again in a couple of weeks. On May the 7th, we'll have a program that will be an online version of the Maryland AI Roundtable. The topic on May the 7th at 4 p.m., that's a Thursday, will be protecting and exploiting intellectual property. We're going to have as a guest then Tarek Naji-Ullah, who is a patent attorney in Baltimore. He's also a TEDCO network advisor. TEDCO is the Maryland Technology Development Corporation. So you can find out information about that meetup and respond online at the Maryland AI Meetup site, or Baltimore Tech if you prefer. So thanks everyone for attending, and see you again at a future program.